Okay, homework 2 is due, and I've just given you homework number 3. You're going to need to submit that on Sunday the 27th. And so we're going to go over a lot of information today. We're going to go over a lot of information today related to reactors. And the majority of the homework assignment that I've given you today is related to reactors. And so if you have any questions, then you need to get those resolved before the break, because I'm going to be actually out of the country. So it'll be difficult for me to meet with you when I'm in India during Eid. Maybe you're traveling as well. So it's just better to get the homework done so you don't have to worry about it. Do you guys have any questions in the back? Any questions? No? Okay. We're going to have a quiz next time in class at the beginning, and so you should definitely be on time that day. We're going to only have about 10 minutes to do the quiz, and so you won't want to waste any extra time. You'll want to have all the time. So any questions about these announcements before we start talking about reactors today? Our last lecture was about kinetics, which is how quickly a reaction happens, or what is the shape of the reaction curve. Does anybody remember what are the different orders of reaction that we were talking about? All right, 0, first, and we also talked about second. All right, so those reaction types are, what they mean is how the reaction curve looks like if you were to graph it. And so for a zero-order reaction, we'd expect linear data if we have time versus amount. For first order, does anybody remember what we need to do to get the data to look linear? Okay, here we have the ln of the amount, and here we have time. And what about a second-order reaction? 1 over the amount, and here is time, and then it becomes linearized. What is the interpretation of the slope over the slope? The slope of the line tells you what? K value. That's right. All right. Sounds like everybody remembers it. That's good. So that was all about reactions. Today we're talking about where the reaction happens. And that's an important thing because different types of reactors have different characteristics. Let's talk about the easiest of them. The simplest kind of reaction is a mixed batch reactor. So imagine we have a tank that is filling with some sort of water that has either a pollutant or maybe it has bacteria, and inside the reactor is where the reaction occurs. It's just a special place where some reactions require oxygen, and so if we fill the tank with water and then we can bubble oxygen, that helps the bacteria to grow. Or maybe inside the reactor it has to be stirred in order for the reaction. So we put it in a special place, and after it's finished filling up, then there's no liquid coming in for a batch reactor during the reaction phase. A batch reactor means that a certain amount is all together the whole time during the reaction. And what do you think this little symbol means here? Mixing. It's mixing. It looks like a propeller somehow. Mixing isn't always like a physical impeller. Sometimes what they would do is just put an air stone, like maybe you've seen for a fish tank. You know, it puts bubbles into the water. If you put that at the bottom of the tank, then that will stir the water as well. There's different ways to stir a reactor. The third phase of a mixed batch reactor is the draining phase. What goes in is called the influent, and what comes out at the end is called effluent, E-F-F, effluent. It seems like you'd call it outfluent, but for some reason it's not that simple. It's effluent. Here are the reaction equations for a mixed batch reactor. These are from your book. This is a table that's taken from your book. And we have zero order, first order, and second order kinetics. Now I'll point out that these are assuming a decay reaction or a consumption. So whatever it is you're keeping track of inside the reactor is going down for this version of the equation. And they're solving for T sub theta. And what that means is a certain amount of time. And so if we wanted to know how long it takes, for example, in zero-order kinetics, for the concentration to go from the original concentration to the final concentration, these formulas are saying the time required is C naught minus C divided by K. So C naught is the original concentration. C is the concentration at the time theta in question. And K is the rate constant that we would get from the slope of the line if we had graphed it. Sometimes you have to find the K. In the homework, I've given you a new homework assignment. Problem 2, let's see. You have to find K because I've given you the data as a table. And so you're going to plot the data using Excel to find K. In problem 1, I'm already giving you the K value. So sometimes it's given, sometimes you must find it. All right. Here's another set of equations for first, second, and zero-order kinetics. And this is rearranging to solve for something slightly different. It's to solve for the concentration at a certain time. So this was concentration at a certain time. So concentration at a certain time, for example, for zero-order kinetics, it's saying C naught minus KT. So just rearranging for T. One thing that I'll tell you is that T sub theta, sometimes we have to calculate the time, and the volume divided by the volume divided by the flow rate can tell you how long water spends inside of a reactor. So we're going to sort of keep this in the back of our mind because it's going to be useful when we talk about other kinds of reactors as well. So you could rearrange this equation to find that. It's just giving you the two different ways depending on what you're interested in. If you're interested in what is the concentration at a known time, or how long does it take, T, to have the concentration go from the initial to the final. Yeah?
What does the T greater than concentration over K equal to 0 second?
It means that if the rate constant is sometimes going to be a little bit unusual, like if the rate constant is so low that the time is greater than the rate constant when it's dividing the initial concentration, then the reaction, there's no reaction. So it just depends on the K value that you're given. We'll see that in today's in-class exercise. You'll see the application of that.
Where did we get this equation? T,
Oh, this? Sort of you can get it just from the units. If you have the volume of a reactor is cubic meters, and the volumetric flow rate is cubic meters per second, think about a tank that's filling up. The water level is going up. So how long it takes to fill the tank of a certain volume is dependent on the volumetric flow rate. So you'd have time, the units would cancel, so what you end up with is base units of time, seconds. So sometimes this T is called residence time. What it means is how long is this reaction happening? What is the time from when it's finished filling and it begins the reaction until the end of the reaction and then it's draining? So T, you can think of it as the residence time, or you can think of it as the reaction time. That's a good question. Are there other questions? Yeah. This? This. Oh, that's a C. Yeah, that's C sub T. It looked like an L. Yeah.
T sub theta, it includes the time it takes for the water to...
So you're wondering about how long does it take to fill the reactor, and maybe the reaction is happening as it...
talking about
Uh-huh.
the time in terms of T sub theta.
What's the what?
Time in terms of
Yeah.
the mixed batch.
Here you assume that the reactor fills instantly, and then it begins the reaction.
T sub theta starts when the reaction starts.
That's right. Yeah. You either assume that the tank fills instantly or that the reaction doesn't start until the tank is full and maybe it starts to stir. It's a good question. So, mixed batch reactor. Here's an example of a mixed batch reactor. This is at a wastewater treatment plant. Now, all of you are enrolled in the lab course with Engineer Akil, right? Yes. Okay. So we are going to go on a tour of a wastewater treatment plant. Has anybody here been to a wastewater treatment plant before? Only one? All right. Well, you're all going to have that privilege. Yeah, there's a very interesting aroma at a wastewater treatment plant, probably you would guess. The one we're going to is close to University City. It's just outside the clock tower roundabout, in fact. As you go towards 311, it's on the left. So here, what we see is that there are 9 different tanks, and these are in different stages of reactions. You have to have, in a mixed batch reactor, if there's always liquid coming in, you have to have more than one reactor because one will be reacting, one tank will be emptying, one tank will be filling, and so that's called redundancy. So here, this may be, it looks like it's getting stirred more vigorously, aeration. This is in an aeration phase. Maybe this mixing is a little bit less intense just to keep the liquid from becoming anaerobic, which means losing all of its oxygen. And then here, this is either they're draining the tank or filling it. And so this is a sequenced batch reactor where there's different sequences and they have many different reactors in order to allow it to, water always is coming in. You know, even in the middle of the night, water is coming into the wastewater treatment plant. And so you have to have somewhere for it to go. Let's see, not that one. I was hoping we could only just do the back. Let's talk about the next kind of reactor. It is called a plug flow reactor. So you can think of it simply as a pipe. Water is flowing through a pipe. It enters the pipe at one end and the reaction begins as soon as it gets into the pipe. Now the water is flowing through the pipe in a way that we assume inside the pipe it is not mixing. Inside the pipe, the water is staying together. And so you can see this little hashed area here. It's considered a plug. And you think that the plug is traveling at a certain speed through the pipe. And so we need to know how long the reaction is occurring. And that depends on how long the water spends in the pipe. And that comes back to this equation. The amount of time it takes to go through the pipe depends on the flow rate and the volume of the pipe. Now, it's not always a pipe. Sometimes it's a pipe, sometimes it's a rectangular channel for a plug flow reactor. We'll look at pictures of real reactors for both of those. But the main idea is that as the water flows through this reactor, number one, it doesn't mix, and number two, it is traveling at the same speed as it comes in as it goes out. Here is the kinetics in order for us to find the time it takes for the concentration to either increase, or in this case, these are for decay reactions. So this is the concentration starting at C naught and decreasing to C sub T. So how does this differ from the equations on the last slide that we looked at, from the batch reactor? It's the same, right? And so the difference between a batch reactor and a plug flow reactor is the plug flow reactor is better for continuous flow. You can have only one reactor and it's okay for water to always be coming to it. If you always have water coming, the batch reactor doesn't work because during the reaction phase no water can come in or go out. And so a batch reactor, as the name implies, is best for a batch of liquid, not for a continuous amount of liquid. whereas the plug flow reactor can take water all the time.
I don't understand. What is the plug contain?
It's just water. It's whatever is flowing through there, and it's not different from the rest of the water. Let me give you an illustration. I'll draw a pipe on the board. Okay, so here is our reactor. It's a pipe, and we have some water. Here we have a tank of water, and it has sugar in it. This is sugar water. We don't want the sugar to be there. We'll talk about why later on, but let's say that the sugar is a bad thing. And so we can get some bacteria to eat the sugar, and then it goes away for us. It's not a problem any longer. So we take the water, and we put it into the reactor, and it is here. And then we also inject the bacteria. So now it's sugar and bacteria, and it's flowing through the pipe. If we have the water flowing slowly, then it won't mix. If we have it going fast, then there will be turbulence and mixing, and it would mix. But we're very careful when we are using a plug flow reactor to have the flow going smooth, and so it doesn't mix, and it stays together as it's traveling through the reactor. And by the time that plug comes out, the reaction is complete. Now there's no sugar, because the bacteria that were in the solution have been using the sugar and eating it, and now it's gone. So your question was, I think, having to do with, like that plug, it's just surrounded by water on both sides, and there's always more water coming in. It doesn't, the water, you can't have air on either side of the water. It's just continuously water keeps coming in and going out the whole time. So what we could say is we connect the tank. Let's draw a larger tank. Here is the tank, and there's a pipe connecting it like that, and then maybe we're taking this to the river. We didn't want to put sugar into the river, so this is sugar water, and here is our bacteria. And so this is the water. This is one batch of liquid that stays together. And so when this batch moves to here, there's new water behind it. It's just always continually flowing through the pipe at all times. No, it's not a filter, because if it was a filter, the pipe would have sand in it or carbon, but it doesn't have a media. It's just an empty pipe, and that empty pipe is where the reaction occurs. It's just a place that we set aside for the bacteria to grow, in this case talking about bacteria. Well, we would have to make the pipe a certain length, or the flow has to go slow enough, and so we have to know what are the kinetics of the bacteria. We would put the bacteria into a tank, and we would find out what is the K value. And if the bacteria eats the sugar very quickly, the pipe doesn't have to be as long. But if the bacteria eats the sugar slowly, we have to make the pipe very long. Good questions.
What is the bacteria?
It's stirred in. As soon as the bacteria and the sugar water come together, you'd mix it and then stop mixing once the water gets into the pipe. Okay, so these are the equations to solve for the time required if we knew the sugar water that's coming in is at some initial concentration, and then the concentration at time t, after the water comes out, we would want it to be below some limit. This would tell you how long the reaction time is needed, T naught. This is rearranging those equations to solve for what is the effluent concentration for a certain fixed time. You notice here it's saying theta. Theta is the same as T. Here we were saying T sub theta. I think actually in your textbook it may say T for these equations rather than theta. I just noticed that the slides, the publisher puts together are slightly different. They're using theta and t interchangeably. So let me just emphasize that. Here, theta equals t, and what it means is reaction time. Okay. And you can find out how long the water takes to flow through the pipe if you know the volume of the pipe. What's the volume of a pipe? What are the parameters that can allow you to calculate the volume of a pipe? Okay, it's the cross-sectional area times the length. So if you know the diameter of the pipe, then it would be pi d squared divided by 4 to get the cross-sectional area. And then the length of the pipe would then give you the volume. Here's a look at two different kinds of real-world plug flow reactors. This is an enclosed pipe on the left, and so water will enter at one end and it flows through, hopefully with as little mixing as possible. A plug flow reactor works best if the liquid isn't mixing up. And so there's things we can do to help so that the liquid doesn't mix, and chief among them is we have the water move slowly. If you have the water moving fast, then there's lots of turbulence. Here's an open channel plug flow reactor. And here in this open channel plug flow reactor, the water enters and is going very slowly. Let me ask you, why do you think they have the curves around the edge, the outside edge of this reactor? Could be. Other ideas like, why do you think they have that gradual transition around the edge? The impact speed? Why would they want to reduce the impact speed? It doesn't mix. They're doing everything they can to prevent mixing because they want the plug to stay together. You have the best performance if the water that enters together stays together the whole time. If it spreads out, then it doesn't work as well. The reaction isn't as efficient if it spreads out. And so if you have, let's look from the top view. Okay, if we have water coming in here and let's see, it would be like this. The water is coming in here and it's going to exit there. So the water is going around. If it's a sharp edge, then there can be a lot of mixing and turbulence when it goes around the corner. But if we have our reactor and it's a smooth edge like that, and we fill it in with concrete, then when the water comes around this corner, it's a very gradual transition for it and there's less mixing. And so you'll commonly see these rounded corners when they're trying to preserve.
So what do you mean by mixing? Like water mixing by itself?
Well, remember we were talking about sugar and bacteria? What's the concentration of sugar at the front of the reactor? High or low? Okay, that's right. So here the concentration of sugar is high. What about the concentration at the end? Low. What we want to do is we don't want the high concentration sugar to mix with the low concentration sugar. We want it to stay separate. And so here, if we have the high concentration pollutant together, the reaction is happening more quickly in first order kinetics. And this goes back to the main idea of first order kinetics. And that is most of the reactions we have in this course are first order. Let me write this on the board because this is a really important point, like why we care so much that they shouldn't mix. Because first order kinetics okay, R is the reaction rate. It depends on two things. Do you remember what are the two things that the reaction rate depends on? K is one of them. And then C, the concentration. And so we want a fast reaction rate. That's good for us. We're engineers, right? We're trying to be efficient. We don't want this reactor to be really large. We want to make it as small as possible. A small reactor means it's less expensive to construct. A small reactor means it's taking up less space. And so we want fast reaction. Because then the reactor is smaller. Okay, so look at this equation. R equals K times C. If we want a big R, then we either have to make K big or we have to make C big. Those are the only two ways you can make it happen. Usually you can't control K. You know, the bacteria, they'll eat the sugar as quickly as they can, but maybe one species of bacteria eats the sugar more quickly than another one. So you have a little bit of control over K by what reaction you're dealing with. But what you have a lot of control over is C. If you make the concentration high in a certain spot, then the reaction rate will be very quick. And so here in this plug flow reactor that's on the screen, at the beginning of the reactor, when we just barely mix the ingredients together, the reaction is happening very fast here because the concentration is still high. But as the concentration decreases later in the reactor, then the reaction rate is slowing down because this is first order kinetics. If you have a low concentration, now the reaction isn't as fast. And so it's best for us if we don't have mixing. That makes it the most efficient reactor possible. Does that idea make sense? We'll come back to this point a lot because it's important. But you know, it would be easier just to have a big tank. They went to a lot of trouble to put this, they call it sometimes a racetrack. You know, like think about if maybe it's a racetrack somehow. It would be easier just to have a big empty tank and just allow the water to come in and mix it up. But that wouldn't be as efficient because it would have all of the concentration together. It's more efficient if we keep the high concentration isolated so that the reaction rate is faster. Here's the third kind of reactor. This is when you just have it all mixed together. It's called a completely mixed flow reactor. There's a few different names for it. Sometimes you'll see this reactor abbreviated like CSTR. You should put this in your notes off to the side. You know, you have the extra space in the notes. Sometimes this reactor is called CSTR, which stands for continually stirred tank reactor. Okay? Sometimes it's called a completely mixed flow reactor, CMFR. Basically, you have the water coming in at a certain flow rate and it's going out at the same flow rate, usually, if it's in steady state. If it's not, if in and out aren't the same, then the water level is either filling or emptying. But in steady state, they're the same, and then the water level stays steady. The influent concentration is C naught, and the effluent concentration is C sub T. Inside the reactor, the entire tank has the same concentration. So C sub T is the concentration coming out, but it's also the concentration in here. The concentration inside the tank is C sub T. Now, what was the nice thing about the plug flow reactor? Like, what's the beauty of it?
It's continuous.
It's continuous. Is this continuous? Yes. Okay. So this is another one that's continuous. What about when it comes to first order kinetics? If we want the reaction to be fast, what should we do? High concentration at the beginning. So we should keep the high concentration separate from the rest of the liquid. So here is C naught. This is the high concentration. It comes in. Does it stay isolated? No, it's instantly mixed. And so the reaction rate is going to be slower in a completely mixed flow reactor than it would in a plug flow reactor. So these reactors aren't as efficient as a plug flow reactor, but they're easier to build. So here are the equations for 0, first, and second order inside of a completely mixed flow reactor. So here again we're solving for the time it takes for the concentration to decrease. This other set of equations is what is the concentration coming out of the reactor after a certain time. Here's a real world completely mixed flow reactor. We'll see this when we go to the wastewater treatment plant. It's a big tank that's getting stirred, and there is water coming in, water going out all the time, 24 hours per day. Okay, you have the in-class exercise. What I'd like you to do is take a look at these three problems. We have a batch reactor for problem 1, a plug flow reactor for problem 2, and for problem 3 we have the completely mixed flow reactor. So all three you're getting to try. You have the equations because you've got the notes there. Is it too small or can you see it? It's pretty small, right? All right. Well, you'll manage. I have faith. What I'd like you to do is work together in partnerships, work together with a partner, and go through and answer these questions. You're trying to find the time in the first one and the flow rate in the second. All right, so go ahead. Everybody got 91.4 hours for the first one, right? Okay, good. So remember, I'm recording this, and so right now it's being recorded. If you want to review the in-class exercise, all you have to do is go to the YouTube and search towards the end of the class, and you can see here's the solution on the video. All right? Here's the solution for the second one. We're running a little bit out of time, so I'll put that on the screen. That's fine. Muted meters per day. It's okay. But let me just show you the solution of the last one. You don't have to furiously copy it down worrying about it, but ooh. All right. So it says 90% removal. If you have 90% removed, how much is left? 10% remains. So the initial concentration is 185. If 10% of that is left, that means the concentration coming out, the C sub T, is 18.5. So that's the effluent concentration. So we're using the formulas for first order kinetics, completely mixed flow reactor. Here is the formula for it to solve for T naught. So the ratio of the inflow and the effluent, minus 1 divided by K. So we find the time, 1.46 days, and then you can solve for the volume by knowing the flow rate. The flow rate is given as 0.15 cubic meters per second. And I think I asked for in days what is the volume. So there it is. Okay. 18,960 cubic meters. All right, we are out of time, so as you leave, please set the in-class exercise on the chair so I can collect them. Here is some papers from last time if you didn't already get that. I will see you on Thursday for our quiz.